Let's begin our first homework 1 help session. I'm Angus, your TA, and today I'm going to help you go through homework 1. And I'm going to talk about how to use GDB specifically and how to build route chain, how to look for functions, disassemblies, and gadgets using tools that are provided in either the VM or the Docker container. And I'm going to kind of walk through the homework workflow and to make sure that we're on the same page. Okay, so we have already covered basic overview of stack smashing. But we only talk about it on paper, and we haven't had a chance to actually build our own payload to exploit vulnerability. So this homework basically provides you a real-world experience in developing exploits that manipulate vulnerable programs into doing stuff that it's not supposed to do. So your GitHub README already provided a detailed overview about of the project steps, and we strongly encourage you to read through it carefully. Pay close attention to important details like when should the ASLR be turned off, and which tasks require you to build payload that is dependent on ASLR base addresses, which task does not, and so on. Okay, so here's the topic that I'm going to cover today. First, I'm going to walk through how to build a route chain specifically and how to find gadget and smash those gadgets together into a functional route chain. And I'm going to walk through the project structure and the task workflow. And finally, I'm going to demo how to use GDB specifically because sometimes when you're building payload, it just doesn't work for some reason. So it's better to look at the program dynamically using tools like debugger. And if you're writing the next exploit, then GDB will be your go-to debugger. And it'll be your friend if you're interested in exploitation in the Linux environment. Alright, so let's begin with route chain and gadgets. So we have talked about route chain already. So now I'm going to walk through it real quick. So a basic route gadget looks like this, right? It contains a pop register and then a return. This is like a strongest gadget that you can get. So what pop register does is that it will pop the value from the top of the stack and store it in the register that you specify. And return is pretty similar. It is equivalent to pop RIP, and you know that RIP is basically the program counter in x64. So what return do is that it will grab whatever is at the top of the stack. Could be an address, could be anything else, but usually it's an address, and then just store it in RIP so your control flow get transferred into that specific address. On the right, there's an example of a route chain that calls execve binsh no. And what this does is that it basically just pop a shell out. And you can see that we're doing Linux exploitation. This pattern, this function is probably your friend, I'll guess, because you're going to, most of the time when you're exploiting vulnerabilities, your go-to goal is to pop a shell from the vulnerability. And yeah. So one of my questions for you is that if you want to call execve function, where should the /bin/sh string and the two nulls stored? Should it be stored on the stack, or should it be stored in some specific registers? Well, you can see that I already hinted you at the answer. So on the right, you can see that the /bin/sh string should be stored in RDI. And the two nulls should be stored in RSI and RDX respectively. So what this means is that you can see that RDI corresponds to the first argument, right? And the RSI corresponds to the second, and RDX corresponds to the third one. And this thing is called calling convention. So calling conventions are basically rules defining how a function should receive parameters, how, like where the return value should be placed into, and so on. So in P1, you won't encounter function calls with like more than 3 arguments, but it is good to know what the calling convention is on Linux. If you want to build like more complicated rock chain, like you want to call a function that takes 7 or 8 arguments, then it's better to know which argument should be stored in which register or on stack. Anyway, so we need at least 3 gadgets to make this execve function call work. And you can see on the right, the 3 gadgets are pop RDI return, pop RSI return, and pop RDX return. So whenever you're building your blockchain, your first thing you need to do is to look for these pop register return gadgets. And once you have those gadgets, all you need to do is to basically just smash it together. So you can see that if you smash pop RDI return and the address of bin.sh together, what this will do is that this will set RDI into bin.sh. And once you got all of the gadgets and the value prepared, smash it together, and you got a rock chain. So yeah, in fact, building a rock chain isn't really that difficult. The difficult thing is to look for the gadgets that you want. And sometimes when the binary is small, you won't be able to get the gadget that you want. So you might need to do some tricks to make that work. But in P1, you don't need to worry about that. There's already all the gadgets that you need is provided in the binary. All right, so now we gotta talk about how to build a rock chain. So now the problem is how to find gadgets. So one thing that you can do is to manually examine the vulnerable program and look for all return values, all return instructions, and see if there's like pop something before it. And apparently this is quite laborious, right? So fortunately, there's already tools that allow you to do so. 2 of the most common tools are RobGadget and RobPer. And I would encourage you to use both if you have the time, because sometimes RobGadget will find some gadgets that RobPer cannot, and vice versa. But in this homework, we're going to be using RobGadget only because it is good enough to find all the gadgets that you need for this homework. Now, once so the output of your RobGadget is right here on the right-hand side of this slide. You can see that this tool will output each of the gadgets listed on the right, alongside with their address listed on the left. And once you got all the gadgets, all you need to do is to smash it together, add the address and any of the required value to the stack, and repeat the process that I just mentioned until your full gadget chain is constructed. Okay, so one hint that I have for you is that basically a function is a large RobGadget. So sometimes don't get too fixated on chaining only the gadgets returned by your tool. Sometimes you can just call a specific function to achieve your goal. Like for example, if you want to print some text out, instead of always constructing the gadget that does system call, that does a write system call or something, you can basically look for functions like putS or printf in your binary, and that will take care for you. So yeah, sometimes you need to zoom out and see the whole forest instead of fixating on specific trees. Okay, mentioned rock gadget tool already. So now I'm going to demo some tools that you might need to use to find gadgets, find function pointer, find strings in the binary. And yeah, so I'm going to demo this real quick. See my terminal. Yeah, it should be big enough, right? Right, nice. Okay, in this, so I got a demo binary which we will be using for this homework section. And so first, assume that demo is a vulnerable program that you want to exploit. Then if you want to look for gadget, you can use rock gadget like that. Rock gadget -- binary and the vulnerable program, which is demo. Rock gadget, sorry. There you go. So you can see that it basically just print out the gadgets, juxtapose the address. And this is used to find, like traditional meaning of gadget, like these cute little chunks of code left in the program. Now, if we want to look for like functions in the binary, then we will going to use another tool called object dump. So basically what object dump does is that it will take a binary and convert that into disassembly. So you can do something like object dump. -D means disassembly, and the program, which is our demo. And you can see that it will just output the AT&T syntax of your binary. And know that AT&T syntax is slightly harder to read because there's like a lot of like percentage, $, parentheses, which makes it kind of aesthetically not appealing. So what we can do is that we can specify -m intel to let it print out your disassembly in a Intel format. There you go. Slightly easier to read. Okay, so this is what the object dump tool can do. Now, if you want to find strings in the binary as opposed to like functions or disassemblies, you can use the strings command, which is also part of the tool part of the binutils tool. So what you can do is that you can specify strings and the vulnerable program like that, and it will just print out strings that look ASCII enough. And if you want to specify its address, you can, not address, sorry, if you want to specify the offset from the beginning of your vulnerable program, you can do -tx, which will print out the offsets alongside with the strings. But be aware that the strings command will output string that has a minimum length of 4. So if you want to search for a string that is less than 4, you need to specify the minimum string length using -n. So if you want to search for that string and maybe like of a length of 2, you can do that. Specify -n2, and there you go. You can see that it print out this kind of like H0, what is this, I0 string, which previously didn't get captured by strings by default. All right, so this is pretty much all of the static tools that you will need for this homework. And a course. You can also do all the stuff dynamically using GDB. And one advantage of using GDB is that it allows you to like look into the memory and look into the basically a bunch of like disassemblies dynamically as opposed to statically, so that it gives you a better insight in terms of how the program runs and at what specific point what like strings are exposed to you. And we are going to talk about that later. Alright, so now I'm going to provide you for some tips that can help you in terms of building your rock chain. So, first tip that I have for you is POT functions. So, I have a question. Is POT function covered in the lecture? No? Alright, I'm going to shortly talk about what this thing is. So POT is basically a shorthand of procedural linkage table. You can think of it as a trampoline that will invoke a function outside of your binary. Like, for example, if you want to call a function called printf, then printf does not reside in your binary, right? It resides in your glibc. So what the compiler will do is that it will generate a POT function called printf at POT, which will like act as a trampoline to call the printf function inside glibc. And I think I'm not going to go through all the details right here because it's slightly complicated. But just be aware that the reason why POT function exists is that the dynamic resolver will help you resolve the function inside the glibc automatically. And this is pretty powerful because for most of the time you do not have the address to printf directly because it resides in libc. If you do, then you can definitely call printf directly. But if you don't, then you can call this function because this function will resolve printf for you automatically. And another benefit for using POT function is that it makes your exploit more reliable. And what I mean by reliable is that suppose that you have a libc leak function address, but it is not printf, it is maybe like puts or whatever. Then you need to subtract the offset of puts and then add the offset of printf in order to get the real address of printf, right? However, in different versions of libc, the offset might be different. And if you're using different distros with different compiler options enabled, it will compile to different libc, so the offset might be different. So if you're using the POT functions to call your function in the glibc, then basically it will handle all of that for you. You don't need to calculate the offsets, and a lot of time it will be wrong because it is stuck to a specific libc binary. Okay. The second tip that I have for you is that when you're passing a string to a function as an argument, you need to pass the address, not the actual data. Like, this is a pretty common mistake made by beginners, and just be aware of that. Like, for example, if you want to store the string hello world, you should not store HELLO blank WORLD directly. If you've done that, then it will call the whatever the string is located at the address of capital HELLO blah blah blah, and apparently that is not a valid address, which will result in a segfault. What you need to do instead is that you should store the value elsewhere, and then provide the pointer that points to your hello world string. So yeah. Okay, tip 3. you should be aware of rogue characters. And what I mean by rogue character is that some characters will make your exploit blows up. Like, for example, if you're using scanf for your string input, then your payload should not contain any of the white space characters like blank, /t/n/v/f/r. And the reason is that they are used as a delimiters. So what this means is that if you're using scanf, then it will chop your input with these values as the separator. If you fail to do so, your payload will get sliced into sashimi, and this is definitely not something that you'll want to encounter. For example, you can take a look at the payload on the left. You can see that I have a string that is hex 402088, right? You can see the 20 right over there. This hex 20 corresponds to the space character, and this is something that you do not want to have in your payload. So instead of using that address, we can try to search for other address that does not contain hex 20, like the one on the right. Hex 405C90 does not have any of the invalid characters that you want to avoid. So the payload on the right is something that you will want to write. Okay, finally, I think this is the most important tip that I will going to give you is stack alignment. And this thing is pretty tricky. So on x86, many of the functions in libc are highly optimized. And a lot of times glibc will contain SIMD instructions or SIMD instructions, like move APS, for example, which stands for move align pack, something. Move align pack, single position, floating point value. Yeah, I think that's it. Yeah. Anyway, notice the A in the instruction. What does A stand for? Align, right? Yeah. What this means is that if there's an instruction move APS RSP, for example, and your RSP is not 16 bytes aligned, then you're pretty much cooked because it will raise a segmentation fault. And unfortunately, this thing happened in many important functions like printf and system, especially system. So if you build your rock chain and you're executing the system function, but your stack is not aligned, you will fail. But the tricky thing is that it depends on the libc that is generated by the compiler. Sometimes, for some versions of distributed libc, it is not heavily optimized, or you're good with that. Sometimes it is optimized, then you're going to hit segmentation fault. And this happens to some functions, and this means that maybe your exploit will work on your local site, but will fail to do so on the remote site. If you're playing CTF, this might be something that you might encounter. And this is one of such a problem. Another problem is that maybe the CTF often gives you wrong libc version, and this also happens a lot. Anyway, so the trick I have here is that when you're building a rock chain and you're calling like system or printf or this kind of non-trivial function, make sure that your stack is 16 byte aligned. Yeah, this is really important. All right. I think that's all I have for some tips in terms of building a rock chain. Now I'm going to walk you through the project structure and the task workflow. All right. So for this project, there's going to be like 4 tasks. Each task requires you to write a payload generator program which will be CX64-task1 to 4. And each of these programs will generate a payload file. So you're not going to use that program to attack your vulnerable program. Instead, it will generate payload file that act as an input to your vulnerable program. Yeah. So for task 1, important thing is that you should turn on your ASLR, because the purpose of this task is to let you write payload that it depends on ASLR address. But if you're using Mac, then you don't need to do anything, because we're using Rosetta, not Rosetta, we're using Docker on Mac, no, Docker desktop on Mac. I think that's a proper terminology, yeah, for this homework. And Docker desktop on Mac will spawn a tiny Linux kernel to be able to run your Docker. And unfortunately, there's like no official way to manipulate that or to change the setting of that lightweight Linux kernel. So if you want to turn on or off ASLR on Mac, it's going to be really tricky and hacky. But fortunately, due to how Rosetta works, you don't need to do anything. The ASLR is already turned on, and yeah. All right, task 1 is a little bit tricky. In one terminal, you should run your task 1 too, and it will spit out a leak address. Then you need to stop doing anything. You should instead open a second tab or terminal and run your attack with your leaked address as the input. Then it will generate your payload, and then you just resume back to your first tab or terminal and specify the file as your attack file to allow you to complete your assignment. So I'm going to show that real quick. Okay. So I already have all these homework done. So I'm not going to spoil my solution, unfortunately, but I will going to demonstrate how to run the task 1 workflow. So here we run task 1. Sorry, it should be task 1 too. And then you can see that there's going to be a address leak right there. And this address is ASLR address. So if you run it multiple times, you can observe that the leak address is different. All right, anyway, so once you run task 1, 2, you start another tab or another terminal, run your task 1 attack, and your task 1 attack should take your stack leak as an input. So in this case, the task leak is this disgusting number. I'm going to specify right here. All right, now it should generate a file called task1-payload. The file name can be anything, but for conventional purpose, let's just call it task1-payload, because this is what they want you to name your child. Yeah. And so if you execute ls-lt, pipe it to head, you can see that task payload is generated. All right, after you run your payload, go back to your first terminal or tab and then specify task1-payload as your payload. And there you go. This is the expected output. It should output your name, the string name, and your name or your ID or whatever, as long as this ID is consistent. I'm going to give you points on that. Yeah. And one thing to note is that after executing this function, executing this binary, I should not see any segmentation fault. Sometimes when we're doing like this kind of exploitation, once we're done with our job and we exit, you're going to see some disgusting segmentation fault stuff. Like spawning a shell, and once you exit, you will hit segmentation fault, and do not want that to appear on your homework. Yeah. So the thing is that after you've done all the nasty things, remember to call exit 0 to terminate your program gracefully. All right. Task 2. All right, task 2. Task 2 is slightly harder or easier, depending on how you would like to interpret it. For task 2, it should not require any input to create the payload file, which means that your payload file should not depend on any ASLR addresses. You should build your payload completely using the gadget that you can find in the binary task 1, 2. And the purpose of this assignment is that you learn how to write reliable exploits. You can see that in task 1, it relies on a stack leak address, and sometimes this is okay. But if you are able to exploit your program in a way that does not depend on any ASLR addresses, then apparently this is a better thing to do, and you should write your exploit that way. So for task 2, the workflow look like this. Pretty straightforward. Okay, task 2. Yeah, for task 1 and task 2, you're going to run task 1, 2. It is the same binary as task 1, and it also leak a stack address, but you're not supposed to use that thing. Okay, you're not supposed to use that leaks stack address. What you're supposed to do is that you should just run task 2 payload. And did I did anything stupid? Was that permission denied? What? Oh, sorry. Task 2 attack. What am I doing? Task 2 attack. All right. Once you run task 2 attack, you should be able to see the task 2 payload generated right here. You should provide that directly as your input to the task 1, 2 binary. So you should do something like that. Task 1, 2, and then provide task 2 payload directly. And boom, there you go. You have a shell. So when I'm grading this homework, I want to see something. First thing is that I want to see 3 lightning saber ID, whatever that means, to be printed out. Actually 4. It will print out 1 for you, and then for the last 3 ones, you're supposed to use route to print them out. And another thing is that I want your shell to be spawned and to be able to execute command like ID. This is my ID and whatever, cat, get my password. I'm not going to cat my password file, but whatever. I should be able to execute common commands on Linux. And the third thing is that after exit, I do not want to see any segmentation faults. So be aware of that. And yeah, that's all I'm going to say about task 2. All right. Let's take a look at task 3. So task 3 is pretty similar to task 1 and 2, and I'm joking. No, it's completely different. Task 3 requires you to overflow some stuff on the heap area. But since heap exploitation is too hard, I'm not going to give you any homework regarding heap exploitation. What task 3 is trying to do is that it has a function pointer that lives in a heap area. And you're supposed to override that function pointer into something else to execute a function that is not supposed to execute. And this is actually the easiest task in this homework. So if you have trouble with task 1 and task 2, you can skip it and do task 3 first. Okay, task 3 should also not require any input to create your payload file because it's too simple. Yeah. And also, I forgot to mention for task 2 and task 3, it doesn't matter if your ASLR is turned on or turned off because you're not supposed to use any ASLR addresses. But when I'm testing task 2 and task 3, remember that I will be testing it with ASLR enabled to make sure that you didn't do anything that relies on ASLR address. All right, anyway, go back to task 3. Task 3 workflow is pretty similar, except that it accepts your input from the arguments of the command line as opposed to standard input. So we were going to run task 3 with cat payload file, which will print out your payload on the command line and then consume that as your input. So all right. Task 3. If you run task 3 directly, it requires you to consume one argument. So let's make task 3. Let's run task 3 attack. And you can see that payload 3 is generated. Task 3 dash payload is generated. So I'm going to run task 3 with cat payload 3 and not payload 3. Sorry. Task 3 payload. There you go. And this is the expected output. I should see this stuff getting printed. The chamber is open. I think this is like Harry Potter reference, but I'm not sure. I don't read Harry Potter, sorry. But yeah, this is the expected output. And that's pretty much all I'm going to check for task 3. So don't worry about the rest of the stuff. And also, you should not end up in segmentation folder or anything. Yeah. All right, the last one, task 4. Task 4 is actually removed in the previous semester, but it got revived because we figured out how to make task 4 work. That is to basically just turn off ASLR. Yeah. And for Mac user, you also don't need to do anything because Rosetta emulates x86 in a way that heap address is not randomized at all. I don't know why that's the case, but that's that. And task 4 is similar to task 3. It requires you to exploit the what's that called? T-cache poisoning attack that is taught during the class. And so basically, you need to be aware of, you need to you can review what T-cache poisoning is about, and if you've done that correctly, then you should be able to get task 4 too. Also, task 4 should not require any input to create your payload file because ASLR is turned off. So you can use hard-coded address. That is completely fine. All right, task 4, let's show it real quick. Task 4, if you run it, it requires you to have 2 arguments, right? Yeah, 2 arguments, right. So let's run task 4 attack, and it should generate 2 files, which is task 4 payload 1 and task 4 payload 2. I mentioned that this file can be anything, but please just name these 2 files so that I know which one should be used as the first argument, which one should be used as second. If you name it to something like SpongeBob and Squidward, I do not have any idea which one should go to the first one, should go to the second. So please name your payload with something that makes sense. All right. So that's one task 4 with cats payload. No, payload. Cats task 1. Task 4 payload 1. Cats task 4 payload 2. What? Oh, sorry, I forgot to disable my ASLR. Yeah, so to disable ASLR, do echo 0 sudo tproc sys kernel randomize vspace. Yeah. There we go. Okay, now ASLR is disabled, and then we run this task. What? Did I do anything stupid? There you go. Sorry. Why am I executing sudo twice? Alright, there you go. Once we disable ASLR, we can see that the chamber is now open. And also, I'm going to grade task 4 depending on whether I saw this output or not. Alright. Yeah, so this is pretty much the workflow of all of your homework. So is there any questions right now you want to ask? Oh, sorry. Is there any question currently? No? Alright. If there's no question, then let's head back to the most important thing today, which is some tips, GDB tips. Okay, so how many people have used GDB before? So everyone. Okay, so what's the point of this session? If that's the case, then I'm going to go through GDB real quick. So GDB is basically a debugger which allows you to inspect what's going on in your memory when you're running a program. Yeah, you can start GDB using this command, and if you have multiple arguments, you can use --args to specify the arguments. And these are some common GDB commands. Basically, there's a cheat sheet. I'm going to go through it since you guys know what this is. All right. Yeah. I think I should just demo this thing. Demo. All right. So where's my button? Okay. So I have added a demo to the repository, and you're not supposed to see any demo in your repo, but this is something I just added, and just for the purpose of this session. So let's take a look at what our demo program is doing. So again, if we want to print out the assembly of the vulnerable program, in our case this will be demo. What we need to do is object -m intel -d demo, and this will print out the disassembly, the assembly. Sorry. All right. So let's run this demo real quick and see what this is doing. Okay, it said it wanted to enter some file. I don't know, try etc issue. Why not? And it does nothing. Okay, try etc password. and boom, segmentation fault. So what is it doing? Let's return back to object dump. Yeah, so I'm not going to analyze all these disassembly for you, but I'm going to tell you what this is doing. So what it's doing is that it will consume a file, read all of the content from the file, and then copy that into a buffer. And the buffer size is too small, so it will cause a buffer overflow. Yeah, so this is pretty much what it is doing. So if we provide our file with the corrected crafted input, then you should be able to exploit that and turn it into something that is not supposed to do. Let's write our payload. I'm going to use a neovim to write my stuff, but feel free to use anything else. Exploit, let's see. All right. Now, I'm going to do something that should be, that's kind of like cheating. I'm going to read, what is that? Exploit.c, what is the file? Let's read. Oh, CS642 -demo.c. Okay. Exploit.c. Demo.c. There you go. I already wrote the exploit. Yeah. This is something that you're going to do when you are writing your exploit. First of all, you need to first build your rock chain, right? So I already talked about how to find gadgets and find address using object dump, using rock gadget. This is something that you need to do first. So pretend that this doesn't exist. Okay, I'm going to just delete all these crap. Oh, sorry. I'm going to delete all these crap. All the way down to here, like right payload. Okay, so this is something that you will probably want to do. First, you create a payload string, which contains your payload. That might be ROP, that might be something else, but in our case this will be ROP because this is a buffer overflow demo. Alright, since we know that this is buffer overflow, right? So what we're going to do is that we will first fill in our payload with a bunch of junk. And the reason is that we want to figure out where the program will crash. So, and the simplest way to do that is to fill your payload with a bunch of crap, like this. For I equal to 0, I less than x maybe 80, I think. Yeah, that's just the length of our buffer, and I plus plus. And then let's do payload offset plus plus equals to A. So in this case, I'm going to use the character A as the junk. So we're expecting that your program crash with a bunch of junk on the stack. And yeah, let's do this. Right. Compile our payload. You can just modify this thing. You know what? I'm just going to think I'm just going to use the demo attack payload already written. CS642 demo 3, where is it? Can't find it. Okay, I think I'm going to just use this as a template. Remove all these things. We said that hex 80, right? Okay, so we basically just fill your payload with a bunch of A's, and then let's run this command. Oh, sorry. Let's make it. All right, so we can hit the make command to generate a demo attack. Then, if we run demo attack, it will generate our payload file. And our payload file will be demo payload. So if we run demo and specify demo-payload as the input, and we can see segmentation fault. So yeah, this is the first step that you want to do. Send a bunch of crap to make your program crash. All right, that's step 1. Step 2, let's figure out what is the offset of your return address. And to do that, you can do sophisticated math. That is absolutely fine if you're a mathy person, but if you're a practical person, you can basically just run GDB and see where it crashes. So I'm going to run GDB. Okay, GDB demo. And yeah, since you guys know GDB, you know which command to start the GDB. Sorry, not start GDB, to start a program. Any idea? Should be run, right? Run. Yeah, the run command should start your program. And enter your file, the demo payload. Alright, so you can see that this is the exact point where it causes segmentation fault. Alright, so now let's run some command to inspect your stack. And does anybody know which command can let you inspect address? Anybody remember it? Yeah, it should be the X command, right? So I'm going to inspect 32 characters, why not? And display as hex of RSP, which is the top of stack address. And we can see that this many junk exists on the stack. And if you calculate carefully, there will be a hex 1, 2, 3, 4, 5, hex 48, right? Yeah, there are going to be hex 48 bytes of junk on the stack. But we're not interested in the number of bytes on the stack. We're interested in what the number of bytes before the stack, right? Because that is the number of bytes we want to pad. So we just do a basic calculation. What is hex 80 minus hex 48? It should be hex 38, right? Yeah, hex 38. So there should be hex 38 number of junk before the current the current stack address. So we know that we are going to need hex 38 number of junk for our padding. So let's go back to our exploit. Originally, our exploit is full of junk. Now we want it to be hex 38 instead of hex 80. Okay, does this step make sense to you? Yeah. Yeah. Calculation? Okay, so we have filled our like payload with hex 80 number of jump, right? Now we see that there are hex 48 number of junk on the stack. You can see that there's like 41, 41, 41, all the way up down to here, right? This is the last one. And you can just do basic counting, like there are 8 of them. So these are 16 A's. So that's hex 10, that's 16. So hex 10, hex 20, hex 30, hex 40, and there are 8 of them remaining, so hex 48. Okay, yeah, so basically just subtract hex 80 with hex 48, and you should get hex 38. If you're not used to hex calculation, then sorry, we can use GDP. GDP can also be used as calculator. You can use P hex 80 minus hex, what is it for? 56. Yeah, if you want to print hex, then you can do P/X, which is hex 38. Yeah, so there's 38 bytes before the crash point. All right. Yeah. Okay. So now let's stop our GDB and compile it again and run demo attack again to generate the payload. This time, if you run demo with demo payload, it does not crash, right? Because we provide hex 38 bits, and we haven't actually override any of the stack address. Sorry, haven't override the return address yet. We only provide the padding, so it doesn't result in segmentation fault. But if you do something like hex maybe 40, let's try hex 40. Then let's see if it crashes. Oh, sorry. Let's make it again. Run the attack and run the demo with demo payload. See, it crashed. So what this means is that there should be hex 38 of your junk following your real ROP payload. Alright, so this is step 2. Okay, now let's do step 3. For step 3, let's construct our payload. So what payload are we going to use? Well, we can take a look at object dump. Again, object dump dash intel dash d demo. And let's browse through the code, and you can see, hey, there's a backdoor. Normally there shouldn't be a backdoor, but there is. So let's try overriding it with a backdoor. Okay, so this step is pretty easy. What you need to do is append your payload with a backdoor function. So let's grab the backdoor function. Where is it? It should be hex 401191. Okay, so let's copy this. And then do uint 64t backdoor equals to hex this thing. Okay, and then we pack it. Yeah, pack is basically a function that I provide for easier purpose. Okay, should be like the address back. No, it should not be address. All right. Offset plus equals to just plus 8, so that I can write it this way to make it more clear. Okay, let's run. Segmentation fault. Segmentation fault. Okay, what happened? 38. Sorry, yeah. Well, that's stupid me. Okay, there we go. Demo tag. There you go. So you can see that this backdoor basically just print out my identity. Yeah, so this is a basic overflowing return address with a backdoor function. And there's actually a name for it. It's called return to wit. And this is like one of the most basic CTF problems that you can get in terms of routing. But can we do better? Yeah, I was hoping that maybe this backdoor function can spawn a shell for us, but apparently it didn't. It just print out your identity and then exit. Okay, so here's the deal. When you observe that it executes your identity, there's going to be some functions that's going to invoke a shell, right? And usually these functions are either system, could be the exec series like execve, execlp, execl, whatever. There's a bunch of different series of exec function that basically do the same thing with different APIs. Yeah, so let's take a look at the disassembly again. So let's go to backdoor, and you can see, hey, it calls execve function. Okay, so now we have execve plot function, right? Remember what plot function, the PLT function does, is that it will act as a trampoline and invoke the execve function in the library, right? So perhaps we can use this function and treat this function as a huge route gadget, right? We can construct payload that fill in the corresponding argument of execve to let it execute something else. And it could be other things like maybe execve cat your password file out. It could be execve spawn a reverse shell, or it can be anything else. Most of the time, when we are doing this kind of exploitation stuff, you want to spawn a shell, because once you spawn a shell, you can pretty much do anything you want. And so let's search for interesting strings inside the binary and see what we can do. So let's do strings demo and pipe it to that and see what it has to offer. All right, so the first thing I'm going to search for is definitely the SH string. So you know what SH is, right? This is basically your default shell, and is usually a symlink to whatever the default shell is on your system. So like in Debian, this will be dash, and I don't know what it is in other distros. Like I know that in Alpine it should be BusyBox, but whatever. So let's search for the string SH, and there you go. You can see, wow, there is a /bin/sh string inside this binary. So maybe we can somehow specify /bin/sh as the first argument. Then it will execute what? Your shell, right? And then it will just, boom, pop a shell for you. Okay, so now we have an attack plan. We want to make the first argument to be this bin/sh string. Then we just take a look at the function signature of execve, and we can see that it allows you to specify nulls for the second and third argument. So yeah, you know that null is basically just 0, right? So yeah, your next step is to look for the gadgets that allow you to modify the first, second, and third argument. All right, so now we're searching for gadgets. use rough gadget. And search for pop, RDI, RSI, and RDX, right? If you don't know which of these register you need to store it in, then take a look at calling convention. But I already spoiled it, and it should be RDI, RSI, and RDX. And take a look at this. Yeah, there's RDI, RSI, and pop RDX return. So yeah, we can use these as our gadget, right? Okay, so I think we have everything, right? Pop RDI allow you to modify the first argument. Pop RSI allow you to modify second. Pop RSI allow you to modify third one. The first argument should be bin sh, which is presented in the binary. The second and third one should be null, which is basically just 0. And we got execv plot function. So the rest of the thing we need to do is to smash all of these stuff together into a route chain. So let's do that quickly. Let's copy this. The first one should be pop RDI, right? Pop RDI return. Okay, so what is the address of pop RDI return? It is this stuff. 40117A. Yeah, 40117A. Let's just copy it and paste it there. And remember the hex 00. Sometimes you forget a hex 00 and wonder why your exploit doesn't work. Yeah. Remember, these are all in hex. Okay, so now we have pop RDI return. Right here, right? Okay. Now, this is the gadget, and we want to specify what should be stored into RDI. And this should be the string of bin sh, right? So our next subtask is to look for the string bin sh inside the binary. And we already demonstrated the strings tool. I'm going to show you how to do that dynamically. So let's run gdb demo. And we will run starts because the difference between starts and run is that start will create a breakpoint at main and run doesn't. So if it hits starts, it will stop at main. Right. So now I want to look for the bin sh string inside the binary. So what we need to do is to use the find command. So find command allows you to inspect values or strings inside your currently running process. Okay, and another command is the info proc map command. Info proc map allows you to basically just dump out your current mapping of your running program. And we can see that your demo program start at hex 40000 and ends at 405000. Okay, so use find command with how many O's? Let's just copy it. This number of O as the starting point, and this address at 40500 as the ending point. And what we need to do is we need to find the string /bin/sh inside it, because we know that it exists, right? So it should theoretically return. Oh, it doesn't. What is this error? Okay, let's try another thing. Let's try /b/i. Yeah, so on. Oh, there you go. Okay. I need to look up the proper command for that, but I thought it worked. But anyway, I'm searching for character /bin, that kind of stuff. Yeah, you can do it both ways, but I think, yeah, I think I may have the command wrong, but whatever. Once we have found the /bin, blah, blah, and it says that it is in this address. So let's bin out. No, it is, I thought there is bin sh in this string. Unable to access or personal device in memory. I have no idea what this is. Okay, anyway, I'm going to try it another way. Maybe I'll just use string. There you go, 3040, okay. And let's see. There should be a string. A 304, sorry. What? What is this slash B? Oh, there you go. I think there's a, yeah, hex 1000 shift. Yeah. Oh, that's interesting. Let me try find again. Find here. Sorry. Yeah, why? How couldn't I find it? That's kind of weird. Yeah, I don't know. I don't know what happened. And it's not supposed to print out this warning actually, but. Now let's try doing it, searching it inside a smaller range and see if that will work. Let's do that. Okay, something is wrong with this version of GDB. It's supposed to find /bin/hs, but it doesn't. Yeah, this is annoying. But anyway, we have found the address right here. Here, right? It's hex 404040, which has the bin sh string. So once we found the string, what we need to do is to do stuff like this, right? Bin sh string equals to this address, which is 404040. And bin sh address, bin sh string. All right. So we have successfully done something that pops our bin sh string into the RDI register. All right, now let's do the same thing for RSI and RDX. So RSI and RDX, which is the second and third argument, is pretty simple. It allows you to specify null. So let's just do something like this. Pop RSI return. And pop RSI is this thing. Here. Oops. super difficult to work this way. Okay. Where's my... Report it this way. And then specify 0 as the argument. So we do this. We just specify 0 here. So hard to type it like that. Why not? Let me just spawn my result. There you go. Okay, magically, let's return back to my already working result. Yeah. So basically, just do the same thing for RSI and RTX. Yeah, and last one will be the SXV function, and yeah, just do the same thing. Just stack them all together, and it shouldn't be a difficult thing to do. All right, and let's try it out. Make demo attack, demo payload. There you go. You have a shell. So yeah, this is how you do wrapping 101. All right, any questions? No? I might need to look up why the find command doesn't work on GDB. It should work, but somehow it doesn't on my GDB version. So if you encounter anything similar, let me know. All right. Thank you for attending this session, and the session is recorded, so if you want to take a look at, if you want to review something, recap something, I'm going to post that on YouTube, and I'm going to post the link on Piazza too. So yeah, that's all for me today. Thank you very much. All right, let me execute ls real quick, to prove that I actually have a shell. All right, thank you. Yeah. Yep. Hi, this is me from the future. I have figured out the issue regarding the GDB find command. So let's start our demo program. Now we're at the beginning of a main function. If you execute the find command right now, then GDB won't be able to find any strings. So let's do that real quick. Yeah, you can see that GDB finds nothing. But if you hit the ni command multiple times and execute the exact same find command, then GDB will find your string now. And we can verify that this is indeed the /bin/sh string that we're searching for. Yep,